So now that we have understood the Bayes theorem, let's return to the Monty Hall problem that I had posed in an earlier lecture. So this is the problem scenario. There are three doors. There are three closed doors. This is showing an open door here. There are three closed doors, and there's a car behind one of the doors, and there are goats behind the other two doors. And the player wants to win a car, and as a first step, the player selects one of the doors. Okay, let's assume for this concrete example that the player selected door 1. Okay, at this point, the game host opens one of the other doors to reveal a goat. Always reveal a goat. So in this case, let's assume that the game host opened door 3 to show a goat. Okay, now the player has a choice of either sticking with 1 or switching to 2, because clearly there's a goat behind door 3, right? And the car may be either behind door 1, which the person originally selected, or it could be behind door 2, which is now a possibility. Okay, so should the player switch, right? Of course, the player can either stick with the original door 1 and say, no, I stick with 1. And then the game host is going to open 1 and we'll see whether it's a car or a goat. Okay, so the player can either stick here or go there. And of course, if the player makes the right choice, the player wins the car. Otherwise, they get to take home a goat. Okay, so what is the best chance for the player to win a car? Stick with the original choice, switch, or doesn't matter either way, right? So this is the scenario. Player selected door 1, host opened door 3. What is the best chance? Which of these three? Okay. Now, most of you, I think, when you wrote down your answers earlier, would probably have said, it doesn't matter because the car can be here, the car can be here. So it looks like it's equally possible that the car is either here or here. Okay, this is what most people think when they look at this problem scenario. And as I had explained, the great mathematician Paul Erdos also thought the same way. Okay, but it's actually wrong. Okay, it's actually wrong. And let's use Bayes' theorem to calculate the probabilities for the car being here and here. Okay, so those are the probabilities that we want to calculate now. Okay, C looks correct, but let's check by using Bayes' theorem. Okay, so let's just use some notation to begin with. Okay, so probability of car being behind 1, 2, or 3 initially, right? That is before anything happened. That's it. Okay, and we call this as probability of C1, C2, C3 equals 1/3. Okay, and we also use the notation probability of HI, right? That is probability that the host opens door I is represented by probability of HI. Okay, now let's come to the scenario where the player selected door 1. Okay, player has selected door 1 and the host has not opened door 3. The host is going to open door 3, but prior to that, what are the probabilities? All right, now player has selected door 1 and the host has to now choose either door 2 or door 3. Okay, and so we can assume that probability that the host opens 2 is 1/2 and probability that host opens 3 is 1/2. Right? We don't know which one the host is going to open. So initially the probability of both of those is half. And of course we already know probability of C1, C2, and C3 are all 1/3, right? Because at this point all three doors are closed. So we don't know anything. Okay. Now what probabilities do we need to compute in order to make a good decision, right? So now what we want to compute is, given that the host opens door 3, what is the probability that the car is at 1? And given that the host opens door 3, what is the probability that the car is behind the door 2? Right? We want to calculate these two probabilities and go with the higher one. Right? If PC1 given H3 is higher, we stick with door 1. If PC2 given H3 is higher, we switch to door 2. So this is where Bayes' theorem comes in. Right? We want to calculate PC1 given H3, and we will try and calculate that based on PH3 given C1. And here we'll calculate this based on PH3 given C2. So that's where Bayes' theorem is going to play a role here. Okay, so what is PH3 given C1? Right, so what does that mean? C1 means the player chose 1. We already know that the player has chosen door 1. What does PH3 given C1 mean? Meaning C1 means the car is behind door 1, right? The host knows where the car is, right? So if the host knows that the car is behind C1 and we have chosen C1, the player has chosen C1, right? Then what is the probability that the host is going to open door 3? Well, both of these doors, 2 and 3, contain gourds. If the car is in C1, 2 and 3 both contain gourds. So the host could open this or the host could open that, right? So that becomes a half, right? So if the car is behind C1, the host may open H2 or H3 to reveal a goat. Okay, so now let's consider probability of H3, which is the door that the host actually opened, right? What is the probability that the host is going to open door 3 if the car is actually behind C2, behind door 2, right? It's possible, right? Because we chose 1, the car may be actually behind 2. In that case, we chose 1, the car is actually behind 2. To reveal a goat, the host has to open door 3. There's no choice, right? Because if he opens door 2, he'll reveal the car, which he doesn't want to do, right? So this probability is 1. And of course, if the car is actually behind C3, the probability that the host will open that is 0. Okay, so now we have the conditional probability the other way, right? We wanted to calculate probability C1 given H3 and probability C2 given H3. We now have both of the reverse probabilities. And using Bayes' theorem, we can now calculate the others, right? So for now we want to calculate probability of C1 given H3. In other words, the host opened door 3. What is the probability that the car is behind door 1? And that is by Bayes' theorem, probability of H3 given C1 times probability of C1 divided by probability of H3. That is Bayes' theorem, right? So probability of H3 given C1 is half. We just calculated that. Probability of C1 is 1/3. The probability initially that the car is behind any of the doors is 1/3 divided by probability that the host will open door 3 is half. We calculated that. Probability of H3 is half. So this turns out to be 1/3. So there is a 1/3 probability that the car is behind door 1 given that the host opened door 3. Okay, now let's calculate the other one. This we know. Probability of C1 given H3 is 1/3. What is the probability of C2 given H3? In other words, the host chose door 3. What is the probability that the car is behind door 2? And again, by Bayes' theorem, it's H3 given C2, etc. Okay, which turns out to be 2/3. Okay, so the probability that the car is behind door 2 is actually twice the probability that the car is actually behind door 1, and therefore we should switch. It's very counterintuitive, right? Because if you look at it a priori, it looks like they're both equally likely. But if you apply Bayes' theorem, it turns out that switching gives us twice the chance of winning the car than sticking with our original choice does. Okay, of course, there is no guarantee that you're going to win the car, but this is the higher likelihood option by a big margin. It's twice as likely. So that's what we should choose. Okay, so that's what I'm capturing here, showing that it's twice as likely. Well, let's look at a simple intuition for this. Okay, we have done a lot of Bayes' theorem calculations and come to a conclusion. What is a simple intuition? Okay, initially, before the host opened door 3, right, when you have chosen door 1, okay, so initially speaking, just after you've made a choice and before the host opened the door, you made a choice door 1. So the probability that the car is behind door 1 is 1/3. And the probability that the car is behind one of the other 2 doors is 2/3. Okay, think of it that way. That you made a choice of door 1. The probability that the car is behind door 1 is 1/3. And of course, the probability that the car is behind one of the other 2 unopened doors is 2/3. Okay. Now, by the host opening door 3, essentially the entire 2/3 has now gone to door 2, right? Because the combined probability of the car being behind either of these 2 doors was 2/3. And clearly the host has opened this door and showed us that there's a goat here. So all of the 2/3 probability has now gone here. Okay. That's another intuitive way of saying that this is actually much more likely than that. Okay, so that's the other way to look at it. There are two reasons why I chose to discuss this particular problem. One, of course, is to use it as a way to illustrate Bayes' theorem, and the whole naive Bayes method is based on Bayes' theorem. So that's one reason I chose it. The other reason I chose it is that when it comes to probability, our intuitions are often quite wrong. And I wanted to show you a very concrete example of a scenario where our intuition is so grossly wrong.